Hello, everyone. This is team number 4, consisting of myself, Michael Diez.
Me, Valerie Thomas.
And me, Agustin Munoz.
Today, we'll be presenting our engine block simulation study case, in which we analyze the piston, piston pin, connecting rod, and crankshaft while using the SolidWorks simulation program. Our goal here was to understand how each part behaves under realistic engine loads and temperatures.
Our project focuses on the four main components shown here: the piston pin, piston head, crankshaft, and connecting rod. For each part, we ran appropriate studies such as compression, bending, torsion, buckling, and thermal analysis to replicate real operating conditions inside an internal combustion engine.
All components were loaded using the same peak combustion force of 47,000 newtons based on a 6 megapascal chamber pressure. Acting on a 100 millimeter piston diameter, this allowed us to compare performance consistently across the entire assembly.
For the piston pin, we focused on bending and shear, since this component carries the load from the piston to the connecting rod. Under the 47,000 Newton load, the pin reached a maximum stress of 169.8 megapascals, therefore giving it a factor of safety of 3.7. Displacement here was extremely small, which means that the pin remains stiff and stable.
We also performed a design optimization study by varying the pin diameter from 50 to 90 millimeters. The optimal result was 60 millimeters, which minimized mass while keeping stress below the allowable limit. This helps reduce reciprocating mass without compromising strength.
Next, the piston was tested under compressive loading with the same 47,000 Newton force. The maximum stress was 31.39 megapascal, well below the aluminum yield strength of 75.8 megapascal, giving the factor of safety of 2.4. Deformation was only a 0.0148 millimeters, confirming the piston safely handles combustion pressure.
We also ran steady state and transient thermal studies. The top of the piston was exposed to combustion level convection while the sides were cooled. The results showed that the max temperature was at 637 Kelvin with a minimum of 135 Kelvin. For the transient state, the working temperature was at 300 degrees Celsius at the top of the piston and 180 degrees Celsius for the rest of the body, with the same convection loads applied from the previous study. The results showed the piston stabilized around 637 to 645 Kelvin, which matches realistic engine temperatures and validates the thermal assumptions used in our mechanical studies.
For the crankshaft, we studied bending and torsion. Since it converts linear piston motion to rotation, in bending, max stress was around 41.8 megapascal, giving a very high factor of safety of 13. Deformation was under 0.008 millimeters, showing excellent stiffness.
In torsion, stress increased to 77.9 megapascals, still far below the yield limit, and with a factor of safety of 6.8. Both studies confirmed that the crankshaft is structurally robust for engine torque and cyclic loading. The connecting rod was analyzed under 3 critical loading modes. In compression, the rod experienced about 261 megapascals of stress with a factor of safety of 2.4, therefore showing good axial stiffness.
The buckling study showed a load factor of 7.03, corresponding to a critical load of 330 kilonewtons, far above operating levels. This confirms the rod is stable against buckling, but bending should be the design focus moving forward.
Finally, the most severe case was bending, where the same 47,000 Newton was applied at 13 degrees angle. Stress rose to 528 megapascal, giving a reduced factor of safety of 1.2. This tells us bending is the governing failure mode for this component.
Overall, all four components performed safely under the peak 47,000 Newton load combustion. The piston and piston pin operated well below their yield strengths. The connecting rod performed well in compression and buckling, although bending proved to be its most critical load condition. The crankshaft showed excellent resistance to both bending and torsion.
To extend durability and improve fatigue life, we recommend increasing fillet radii, refining mesh density in high-stress regions, and smoothing sharp transitions across all parts.
In the future, incorporating fatigue modeling, manufacturing limits, and additional optimization variables will help further improve the balance between weight, strength, and durability. Thank you for listening.
Yay!
Yay!
Thank you. Here are our references.